Hi everyone, today we're going to learn about free energy and the equilibrium constant, K. That the student is able to express the equilibrium constant in terms of ΔG0 and RT and use the relationship to estimate the magnitude of K and consequently the thermodynamic favorability of the process. Now under non-standard conditions, the Gibbs free energy of a reaction is equal to ΔG0, the Gibbs free energy at standard condition, plus RT, natural log of Q, where R is the ideal gas constant equal to 8.314 joule per mole per Kelvin, and T is in the temperature in Kelvin, and Q is the reaction quotient. It can be expressed as partial pressure of a gas or concentration of a solute in molarity. Under standard conditions, quotient is equal to 1, so natural log of 1 is 0. So delta G of the reaction is equal to delta G0 of a reaction. Practice problem number 1. Calculate the Gibbs free energy at 298 K for the making of ammonia, given the partial pressure of ammonia is 0.5 atm, nitrogen 1 atm, and hydrogen 3 atm. Now remember, at standard conditions, the partial pressure would have been 1. Now the condition has been changed to non-standard. So we set up the quotient expression, which is partial pressure of ammonia raised to power 2 over the partial pressure of nitrogen and the partial pressure of hydrogen raised to the power 3. Then we substitute the pressure into the expression and find the quotient to be 0.00926. Now, the delta G0 of the reaction at standard condition, and we look up value from the book, is equal to negative 32 K kilojoule. That's equal to 2 moles of the ammonia minus that of the reactant. So reactant is nitrogen and hydrogen elements. This delta G0 is 0. Now we can then calculate the delta G at non-standard condition by putting into the delta G0 at standard condition plus R times T, natural log of Q. And this is ended up to be negative 44.4 kilojoule. Now because it's a negative sign, reaction is thermodynamically favorable. You may want to pause the slide for a minute so that you can really understand my calculations. Now we can explain this by Chaterlier's principle. Since we are decreasing the partial pressure of ammonia from 1 to 0.5 atm, while we are increasing the partial pressure of hydrogen from 1 to 3, that means the quotient is less than 1 because there's less product compared to reactant. Therefore, the system will shift to the right to go forward to increase more ammonia. Therefore, the magnitude of delta G will become negative and becomes more thermodynamically favorable. Practice problem number 2. Write the chemical equation when bromine liquid evaporates to form bromine gas. So here's the equation. What's the value of delta G0? So we go to the book. At equilibrium, delta G is equal to 0. So delta G0 is minus RT natural log of Q, where quotient is 1, so delta G0 is 0. Estimate the boiling point of bromine liquid. Because delta G0 is 0 at equilibrium, so delta H0 is equal to T delta S0, or temperature is enthalpy change divided by entropy change, or 30.9 kilojoule for the enthalpy change from your book. And we calculate the enthalpy change from your book, which is 93.3 joule per Kelvin, converted into 0.0933 kilojoule per Kelvin. Remember, you can look up your book to find these bromine gas and bromine liquid for the enthalpy and entropy change, different values. Now we calculate temperature, which is enthalpy divided by entropy, and we get 331 Kelvin, or 58 degrees C. That's the boiling point of bromine at equilibrium. The relationship between Gibbs free energy at standard condition and K, the equilibrium constant. At equilibrium, quotient is K, delta G is 0. So delta G of the reaction is equal to delta G0 plus RT natural log of Q. So now we can derive a new equation that delta G0 is minus RT natural log of K, or natural log of K is negative delta G0 over RT, or K is equal to the E raised to the power of negative delta G0 over RT. You may want to pause the video for a moment to understand the derivation of the formula. Now, if the delta G0 is negative, that means the K is greater than 1, products are favored. If delta G0 is positive, meaning equilibrium constant less than 1, reactants are favored. If delta G0 is 0, then equilibrium constant is 1, the reaction is at equilibrium. Let's connect thermodynamics to equilibrium. The magnitude of K, the equilibrium constant, can be estimated from the equation natural log of K equals to negative delta G0 over RT. At room temperature, notice that R times T would be a very small number, which is equal to 2.4 kilojoule per mole. Now we can then estimate this delta G0 relative to RT. When the delta G0 value is much greater than RT, the thermal energy, K could be very small if the delta G0 is positive. That means reaction is not thermodynamically favored. Or another way is that K can be very large if delta G0 is negative. That means reaction is thermodynamically favored. Now we need to keep this in mind. When the delta G0 is approximately equal in magnitude to RT, K is nearly 1. We can use Gibbs free energy to predict 1. The direction of chemical reaction. 2. The amount of energy available from a reaction. And 3. The equilibrium position of a system. But remember, Gibbs free energy in thermodynamics provides no information on rate or chemical kinetics. In some cases, thermodynamically favored process may proceed at extremely slow rate. They are under kinetic control, often having high activation energy to overcome. In the biological applications, when delta G0 is less than 0, the reaction is termed as exergonic and spontaneous with a net release of free energy. An example would be cellular respiration. If delta G0 is positive, reaction is termed as endergonic and non-spontaneous with free energy absorbed. Examples are protein synthesis and the sodium-potassium ion pump, which drives our nerve and muscle contraction. To summarize what we have learned today, students have to learn how to calculate free energy under non-standard conditions. They learned how to express the equilibrium constant in terms of delta G0 and RT, the thermal energy. We used the above relationship to estimate the magnitude of K and the thermodynamic favorability of the process. And finally, we learned about the biological application of delta G0. I hope that you have found this video helpful to you. If you like it, please give us a like. And I look forward to seeing you in the next module.